Hello? Sorry. Hi, everybody. So welcome back from the break. I'd like to introduce Professor Brian Kulis, who's Associate Professor in the Electrical and Computer Engineering Department here. And Brian's going to tell us about his work on rich deep models for images, text, and music.
Thank you, Kate. So on the schedule, the title of the talk was something like recent advances in machine learning or something. So I changed the title to something only marginally less vague. So my area is in machine learning, and I work sort of broadly in machine learning. I work on algorithms mainly, but I also do applications in various areas. So I wasn't sure exactly what I wanted to focus on. And so what I think I'm going to do is I'll kind of mention a few high-level kind of ideas or projects that we're working on, and then I'm going to focus on one of the projects that we've been working on lately in the area of music generation. Okay, so as many of you know, machine learning has become crucial to lots of different areas, and a lot of what machine learning is focused on, and what my research is largely focused on, is combining large sources of data with rich models to produce interesting analysis. One of the areas that I spent a lot of time working on and was mentioned in previous talks is the nearest neighbor problem. So the similarity search problem, as was discussed by Stan in the last talk, we have a database, we have a query, and we want to find the closest, say, image in the database to the query. And this is something that I spent many years working on in different aspects of this problem. One aspect of the problem is the metric learning problem, which is the problem of how to actually compare objects. How do we actually compute a notion of similarity, distance, metric, etc., between pairs of objects if we know something about the underlying metric? The other part of this problem that I worked on a lot is the hashing problem, which Stan talked about, which is how do we efficiently search a large database so that we don't necessarily have to scan through the entire database to find the most similar objects to the query. Another area that I've spent some time working on is what I call small variance asymptotics, which is a way to design rich algorithms that are inspired by probabilistic models. So if you look at, as an example, if you look at clustering, and you take a Gaussian mixture model, and you ask what happens when the variance in that model of each cluster goes to 0, you get the k-means problem. Okay? And this same idea actually applies in a lot of other cases. So for example, in dimensionality reduction, you can take a probabilistic model, which is probabilistic PCA, shrink variance and get PCA. You can do it in classification, structured prediction, and so on. And in fact, a lot of the sort of workhorses of modern machine learning, things like PCA, k-means, SVM, etc., can be viewed as arising from a statistical or a probabilistic model with a variance that's gone to 0. So the question that I've been spending a lot of time on is what happens when you take this idea and you apply it in richer settings. For example, if you apply it to a non-parametric model or a deep learning model, what kind of asymptotic results can you get, and what can you say about those resulting models? Okay, so that's another area that I've been looking at. And then the third sort of general theme of my research has been to look at different directions in deep learning. Okay, and there's various sort of sub-projects within deep learning that we're interested in. The one I'm going to focus on is some work in music generation. But I'll just briefly mention a couple of the other ones just to kind of give you an overview. So one of the problems that we're interested in is unsupervised deep learning. So how do we do deep learning with zero supervision? And as a sort of canonical example of such a problem that we might be interested in, we've been looking at the unsupervised image segmentation problem. So given an image, can you segment that image into its corresponding parts? My student Shide will talk about this later today. She's going to give a short 10-minute talk on the architecture that she's developed, which we call Wnet, which is it's essentially an autoencoder with a fully convolutional network, along with a clustering loss that's put at the embedding layer. And it actually gets state-of-the-art results in terms of both segmentation and contour detection. Okay, so I'll let her talk about that. Another area we've been looking at on a very different topic is social media analysis. So we've been looking at a data set of Facebook status updates, which includes about 13 million status updates. And we can ask various questions and do various analyses on this data. For example, can we predict somebody's gender by their Facebook status updates? And our results, which show about 91 to 93% accuracy, are state-of-the-art for gender prediction. That's with character level CNN of up to about 70 layers. We can also get state-of-the-art on a number of other tasks in social media prediction, including predicting religious identity, political affiliation, personality, and others. And in many cases, you don't even need a deep learning model. You just need a simpler, shallow model. Okay, so what I want to focus on for the rest of the talk is some work, and this is joint work with Rachel Manzelli, Vijay Thakkar, and Ali Sai Kamari, is work on generating music using deep learning models. Okay, so the motivation for this project, we became interested in this area of creative AI. So if you look at, like, for example, if you go to the NIPS conference, they have these contests with creative AI, producing artwork using AI algorithms. Creative AI has moved its way into various domains, and one of the domains that we see it more and more is in the music industry. So there are actually a number of albums that have been created recently that actually utilize AI techniques. In fact, the 4 at the bottom are albums that were created using techniques from AI. Now, most of the time, the idea is not to replace artists, but rather to augment the artists and augment the creative process. So if an AI engine can sort of suggest melodies or augment sort of that kind of creative process, it will actually help them create music. AI has also been suggested as a way to generate certain kinds of music content. So, for example, companies like Spotify have noted that when people listen to music, oftentimes they're listening to it in the background while they're working, and all they really want to listen to is sort of some very gentle, sort of simple, background music. And rather than pay artists to compose this music, which is quite expensive, perhaps there's a way to generate that kind of background music automatically. Okay. Now, in the field of automatic music generation, there's a couple of different, broadly speaking, there's 2 different ways that people think about generating music. One is called symbolic audio models, and the other one is raw audio models. Symbolic audio models focus on generating music at the note level. Okay, so if you think about, if you're familiar with MIDI, MIDI music is just a sequence of notes. And so oftentimes symbolic music models work on MIDI, or they work on similar such audio formats, where you train a model by giving it a bunch of notes for certain songs, and then you generate new notes. Now, after you generate those notes, you then have to, those would have to be interpreted by a human or played by a synthesizer or what have you. Okay? But those are sort of relatively simple to get training data for and to train. On the other hand, there's also raw audio models. Raw audio models actually work on the direct raw audio waveforms themselves. So, if you're looking at something like 24 kilohertz audio, say 16-bit audio, you would be generating 24,000 times a second, and you would be generating a 16-bit prediction at every 24,000 times to get a second of audio. Okay, and so these models are much more complex because now you're talking about a larger space of predictions. Okay, one of the models that's been suggested for raw audio for music is a model called Wavenet. This is a model that was generated for speech applications. It was actually generated for speech synthesis and speech recognition applications. And it's actually the best speech synthesis model as far as I know, and it's used in the Google Assistant. Okay, so it can do things like text-to-speech. So if I have a sentence, it can translate that from text to speech. In fact, it's used in, as I said, it's used in the Google Assistant. They now have lots of different voices that they've trained it on. So, if you want to have your Google Assistant use John Legend's voice to tell you, how to get where you're trying to go, you can now do that with basically Wavenet technology. So the way Wavenet works is it's we have an audio waveform. It's just a one-dimensional signal, and it works as a one-dimensional convolutional neural net. And it uses a special kind of one-dimensional convolution called the dilated causal convolution. Dilated basically just means that every layer in the network, the receptive field doubles, and causal means we're trying to predict the next sample of audio given all the previous samples of audio. So causal means the convolution is only expressed as based on the previous samples. Okay, so you end up getting a convolutional net that looks like the figure here, and you can basically take that and build it into this rather complex architecture that's typically between 50 and 100 layers of these convolutions, along with gated activation units as well. Okay, so we applied. The first thing we did is we applied Wavenet. We wrote Wavenet. We applied it to the problem of music generation. So this is just vanilla Wavenet. We trained an 88-layer model for about 300,000 iterations, so that took several days. And we trained it on Chopin nocturnes, which we got from YouTube. And then based on that model, we could then generate new audio. And the model that we get generates audio. Let's see if this works. That sounds like that. Going. So it generates sort of unstructured music. It sort of sounds like someone's improvisationally playing music, but it captures sort of the right sound. It sort of sounds like a piano. So the architecture that we worked on is our interest became, how do we combine these two kinds of approaches to music generation? So Wavenet is is a raw audio model. Can we incorporate now a symbolic audio model that helps us to capture longer term dependencies in the music, things like melodic structure, which you don't get with vanilla Wavenet? So to add structure to Wavenet, what we did is we added another input into the Wavenet, which is going to be the corresponding to the melody of the music, and that melody is ultimately going to be generated by a symbolic audio model, which we used as an LSTM. Okay, so we changed the architecture. Now we have, instead of just inputting the raw audio form, we have actually two inputs, one corresponding to the raw audio and then the other one corresponding to the melodic structure. And that model otherwise is very similar to the original Wavenet model. Okay, and so what you can do with that model is you can now train it, instead of just giving it music and having it sort of learn the structure of the music without any additional annotations. This model would take music along with the notes that are being played at all time steps of the music, and it will allow you to now give it a melody and say, play this melody using the instrument that it was trained on. So as an example for what that means, we trained several models, but the one I'll play here is a cello model. Okay, and it was a shallower network. It was a 31-layer network. So the cello model is trained, and when we train it, we provide annotations of the notes that are being played, and then we can now give the model a melody and say, okay, generate the cello playing this particular melody. So here's a C major scale. That's just MIDI. And now we can say, okay, we'll play this with a cello. It's a little noisy. Turn that down. So that's played with a cello model. And then it follows the melody. And so you can do other things. You can do, happy birthday. I think I'll skip due to time. Yes. So then you can start doing things like you can edit raw audio. You can take a piece of music that you have recorded and you can change the notes and regenerate the audio with the changed notes, and that allows you to edit an existing piece of audio. So for example, this is an unedited cello, and this is when we change some of the notes. Generate the audio, play the new melody. Okay, we can also evaluate this. So we can look at, it's difficult to evaluate these models because they're subjective, but we can evaluate them in one way by saying how well do the raw audio waveforms match the underlying notes that we're trying to have the thing produce. And so you can do different correlation metrics of the raw audio with the underlying notes that it's producing, and you can get numbers that way. You can, and here's another visualization of different notes that are being played versus the raw audio. Now, to actually create novel sort of end-to-end models, what we do is we actually want to create a melody from automatically. And so the sort of the full model, what it does is it treats that second input, which is the melody input, it treats that as coming from a symbolic audio model. And so we use an LSTM, something called the biaxial LSTM. That biaxial LSTM generates the melody, which is then fed into the Wavenet. So the final sort of model that we actually use has an LSTM on the left that's generating a melody, a symbolic audio model. It generates a melody that's fed into the Wavenet as a local conditioning, and then that local conditioning conditions Wavenet to play the melody that the LSTM is producing. Okay, and so this gives you this sort of end-to-end model of generating music that, unlike the original Wavenet, which has no melodic structure, actually incorporates longer-term structure. So we have various examples that we have on our webpage, which you can get, see from link to from my webpage. Okay, so some of the stuff we're doing now with this, we are interested in incorporating advances in the Wavenet technology. There's a new version of Wavenet that's actually real-time, so it actually does real-time generation. Our model is not real-time. We're also interested in how to harmonize multiple networks. So how can we generate, say, a cello model, a piano model, a violin model, and bring them together into one sort of piece of harmony. And then we're looking at other kinds of problems as well. So thank you very much, and I guess there's no time for questions, is that right?
Well, panel right after.
Okay, the panel, which is now. Okay, thanks.